All right, in this video, we're going to continue our discussion of forces by looking at Newton's second law as well as contact forces, with particular attention to the normal force and friction force. So to begin, we can define Newton's second law as the acceleration of an object is directly proportional to the net force and inversely proportional to its mass. We can write this as a proportion right here, where you can see acceleration is directly proportional to the net force and inversely proportional to its mass. Generally, this equation is rearranged to get this famous version where you have the net force is equal to ma. This is definitely an equation you want to know for the MCAT. And what's helpful about this equation is it also tells us what are the units for force. So we can see here it's mass times acceleration, so that means that the units are going to be given by the product of those four, mass and acceleration. So we know that mass is a kilogram and acceleration is in meters per second squared. This tells us that those are the units for force, a kilogram meter per second squared. And we actually call this a Newton. And a Newton is denoted by the capital letter N. So you want to keep in mind what a Newton is and what it is in terms of the basic SI units, kilograms, meters, and seconds here. All right, so to better understand how Newton's second law, let's take a look at a couple examples. So here we're asking the question, which object experiences greater acceleration? In our first example, we have two objects with the same mass. The first object experiences a net force of 10 newtons to the right. The second object experiences a net force of 20 newtons to the right. Now, based on Newton's second law, we know that the acceleration of an object is directly proportional to the net force. So since this object on the right experiences a greater net force, it will experience a greater acceleration. Now, this shouldn't come off as being a huge surprise because if you push with a weaker force, you're going to get less acceleration. If you push with more force, you're going to get greater acceleration. All right, so in our second example, we have two objects. The object on the left has a smaller mass than the object on the right, which has a larger mass. We're applying the same net force on both objects. So they're both experiencing a net force of 10 newtons to the right. So here, what we know is that the acceleration experienced by an object is inversely proportional to its mass. So in this situation, the object that experiences greater acceleration is going to be the one with the smaller mass, which is going to be this object on the left. Again, this isn't too surprising because you also know between pushing an object with more mass and versus pushing an object with less mass, that object with a lower mass is going to be easier to push. So by applying the same force on both objects, the object with lower mass is certainly going to accelerate more. All right. So that's how Newton's second law works, and again we're going to look at many examples where we apply both Newton's first law and Newton's second law. So before we look at those examples, we do need to talk more about the different forces that you will see on the MCAT. And we can divide these forces as contact forces or non-contact forces. And the difference is just whether or not direct contact is required for that force to occur. So of course here we're talking about contact forces. These are forces that do require direct contact to occur. This certainly involves forces like a push. So if you push a box, you cannot apply your force unless you're in direct contact with the box. Now, contact forces are generally divided into perpendicular components. And we've talked about this. We often want to divide forces in different directions in our free body diagrams so that we can isolate the motion in different directions. We can just consider what is the net force in the horizontal direction to know how fast our object is going to move left or right. We can also look at the net force in the vertical direction to know what is going to be the acceleration up and down. So Here, when you're dividing the contact force into different components, the different components are the normal force, which is going to be the component of the contact force perpendicular to the surface, and friction force, which is the component of the contact force parallel to the surface. So we can consider an example here if we're looking at the contact force of a mass on the inclined plane. Now, our object of interest is the mass, and it is in direct contact with the inclined plane, so it's experiencing a contact force. We can draw in the two contact forces, or the two perpendicular components of the contact force. You have the normal force, F of n, which we can see here is perpendicular to the surface. You also have friction, which is parallel to the surface. So this is what we mean by the contact force is divided into the perpendicular components of relative to the surface. So again, friction is parallel to the surface, normal force is perpendicular to the surface. Now, of course, these are not the only forces acting on the object. There is also a non-contact force, gravity, which is acting straight down. But we'll look at that in the subsequent video when we introduce non-contact forces. All right. Now, while we're talking about the friction force, you do need to know more details about how friction works on MCAT. In general, there are two types of friction. There is kinetic friction and there is static friction. The difference between these two types of friction is just whether or not your object is in motion. So if your object is in motion, like a hockey puck sliding across ice, then you're looking at kinetic friction. And the equation for kinetic friction is equal to mu sub k times the normal force. In this case, mu sub k is the coefficient of kinetic friction, and this is going to depend on the two objects in contact with each other. So in the situation that I just described, it's going to be the hockey puck with the ice rink. And that's going to give you some coefficient of kinetic friction. However, if the hockey puck was on a different surface, for instance, if you're looking at hockey puck on concrete, then you're going to get a different coefficient of kinetic friction. Similarly, if you put another object on the ice rink, if you put a block of wood, so then you have wood on ice, and that again is going to give you a different coefficient of kinetic friction. So again, it depends on the two objects in contact with each other. Our other type of friction is static friction. This is when your objects are not in motion. A simple example of this is if you have heavy furniture in your home and you're trying to push it. All right, if it's very heavy and you don't apply enough force, your object's not going to move, and that's because of the static friction. The equation for the static friction is it's less than or equal to mu sub s times the normal force. So here, mu sub s is the coefficient of static friction. Again, this is going to depend specifically on the two surfaces in contact with each other. You'll notice here, though, that the equation is not just equal to that value. It's less than or equal to this value. And that's because the product of the coefficient of static friction with the normal force, that gives you the maximum force of static friction. All right, that's the maximum force that friction can apply to prevent you from moving that object. However, if you don't apply a force that strong, the static friction doesn't have to be that large to prevent motion. For instance, if you push a box with a force of 50 newtons and it doesn't move, that means static friction must be 50 newtons as well, equal in magnitude but opposite in direction. However, if you get tired and now you only push with a force of 30 newtons, the box doesn't have to exert a static friction of 50 newtons anymore. Now it only has to apply a force of 30 newtons to cancel out the force that you're applying. So essentially the static friction is as much as it needs to be to prevent motion, though there is an upper limit. So if you apply a force greater than the maximum force of static friction, then your object will start moving. And one other thing to keep in mind, and that is generally the coefficient of static friction is going to be greater than the coefficient of kinetic friction. And this essentially just means that it is harder to get an object to start moving than it is to keep an object in motion.